Okay, let's unpack this. For years, if you were tackling sequence tasks, like translating languages or generating text, you probably relied heavily on recurrent neural networks, LSTMs, GRUs, that sort of thing.
Uh-huh. Or maybe convolutional networks sometimes.
Right. And if you were really pushing the envelope, you'd usually bolt on an attention mechanism to help the model focus. Yeah.
Exactly. Those older models, the recurrent ones, they processed sequences one step at a time.
Yeah.
They'd build up a representation based on what came before, and the current input, inherently sequential.
And that sequential nature, that was a real hang-up, wasn't it? Especially for efficiency.
Totally.
It really bottlenecks parallelization during training, particularly with longer sequences. You're just stuck waiting for the previous step to finish.
That's the core problem.
Hmm.
Now, convolutional sequence models like ConVS2S or ByteNet, these were architectures using convolutions for sequence stuff.
Hmm.
They could compute representations for different parts of the sequence in parallel. That was better.
Okay, so some parallelization there. But they had their own issues.
Yeah, they struggled a bit with learning dependencies between positions that were far apart in the sequence, and it required stacking up quite a few layers. The path the information had to travel still grew with distance.
So you had RNNs struggling with parallelization, CNNs needing deep stacks for long-range stuff. And attention. Attention was already seen as powerful for relating any two positions, no matter the distance.
It was, but it was almost always used on top of these recurrent or convolutional-based models, like an add-on.
Okay, which brings us to this paper. Attention is all you need. And it proposed something pretty radical at the time.
Extremely radical.
Yeah.
Basically, what if you just got rid of recurrence and convolutions entirely? What if you relied only on attention mechanisms?
Just attention. And that's our mission for this deep dive. We're going to jump into this groundbreaking paper, really understand the transformer architecture it introduced.
And see how it managed to get state-of-the-art results in machine translation while training way faster.
Exactly. And how it also turned out to be surprisingly good at other things, like parsing, all powered by just attention. Let's get into it.
So, like you said, the core problem the paper was trying to solve was the limitations of those previous sequence models. Recurrent models process sequences step by step. The hidden state at one position depends on the previous state.
Yeah, it's like reading a book one word after another. You can't really get to word 5 until you've processed word 4.
Precisely. And that step-by-step computation means you can't process different parts of the same input sequence in parallel during training. You have to wait. That's a huge bottleneck for big data sets and long sequences.
And the convolutional sequence models like ConVS2S, you said they did parallelize. They computed features for all positions at once.
Yes, they did. But linking two words far apart, say at the beginning and end of a long sentence, that information still had to filter through multiple layers of convolution.
Okay, so the path length for information still depended on distance, maybe logarithmically instead of linearly, but still.
Right. And capturing those long-range dependencies, like a pronoun referring back to a noun way earlier, it's absolutely crucial for understanding language.
And the existing attention mechanisms were good at those long-range links, but they were always sort of secondary, sitting on top of an RNN or CNM.
They weren't the fundamental building block.
Yeah.
So the attention is all you need. Paper just said, forget the RNNs, forget the CNNs. Let's build a completely new architecture based purely on attention. They called it the transformer.
Okay, structurally then, how does this transformer actually work? What does it look like?
Well, at a high level, it follows the classic encoder-decoder pattern. You see this a lot in sequence-to-sequence tasks like translation.
Right. The encoder takes the input sentence, chews on it, turns it into some high-level representation.
Exactly. And then the decoder takes that representation and generates the output sentence, word by word, essentially.
But instead of LSTMs or convolutions inside the encoder and decoder, what did they use?
Stacks of layers based on, well, self-attention and simple feed-forward networks. The encoder is a stack of n equals 6 identical layers in the base model.
Okay, 6 layers. And each layer has what inside?
Each layer has two main parts, or sublayers. First, there's a multi-head self-attention mechanism. Second, there's a position-wise, fully connected feed-forward network. Simple as that.
And critically, for training deep networks, they use residual connections and layer normalization around each of those sublayers, right?
Yes, absolutely crucial. Keeps the gradient slowing and stabilizes training. And the output dimension of these layers, the sort of width of the representation for each word, is D model equals 512 in the base paper.
Got it. So the encoder is 6 layers of attention and feed forward. What about the decoder? Similar.
Pretty similar structure, yeah.
Hmm.
Also a stack of 6 identical layers. It has those same 2 sublayers from the encoder, the multi-head self-attention, and the position-wise feed-forward network.
Okay. But you said similar, not identical. What's the
It
difference?
adds a third sublayer in between those two.
Uh-huh. And that third one must be the connection point, right? Linking decoder to encoder.
Exactly. This third sublayer performs multi-head attention over the output of the encoder stack. This is how the decoder, when it's deciding the next word, can look back and attend to any part of the original input sentence representation. Super important.
Makes sense. It needs to know what it's translating from. Okay. And there's another key trick in the decoder's own self-attention layer, isn't there? Something about looking ahead.
Yes, crucial point. The self-attention in the decoder uses masking.
Masking.
Yeah, it prevents any position in the output sequence from attending to positions that come after it. Think about it. When you're generating text, say word number 5, your prediction can only depend on words 1 through 4 that you've already generated.
You can't cheat and look at words 6 or 7.
Exactly. You can't see the future. This masking enforces that autoregressive property, making sure the generation happens sequentially, one word based on the previous ones.
Okay, so the high-level architecture is stacks of these self-attention and feed-forward layers, plus that cross-attention connecting encoder to decoder in the decoder stack. Let's really zoom in on that attention mechanism now. What is an attention function fundamentally in the way this paper defines it?
Okay, so at its core, an attention function takes 3 things: a query and a set of key value pairs. Think of them all as vectors.
Query, key, value, Q, K, V.
Right. The function computes a score based on how compatible the query is with each key. These scores are then used to calculate weights, usually via a softmax, and the final output is a weighted sum of the values, where the weights come from those query key compatibility scores.
So it's figuring out how much attention the query should pay to each value based on the keys.
Precisely, and the specific type they use in the transformer is called scaled dot product attention.
Scaled dot product. Okay, break that down.
So the inputs are your queries Q, keys K, and values V. First, you calculate the dot product of the query vector with every key vector.
Okay, measuring similarity.
Then, and this is the scaled part, you divide each of those dot products by the square root of the dimension of the keys. Let's call it dk.
Right, you mentioned D model was 512. What's DK usually?
We'll get to that with multi-head, but the scaling is important regardless of the exact dimension.
Okay, so scale it, then what?
Then you apply a softmax function to those scaled scores. This turns them into weights that all sum up to 1. Positive weights.
So now you know the proportion of attention to pay to each value.
Exactly. And the final step is just multiplying those weights by their corresponding value vectors and summing them all up. That's your output vector.
Okay, but why divide by the square root of DK? That seems like a very specific detail. Is it really that important?
It actually is, yeah.
Mhm.
They found that when the dimension of the keys, dk, gets large, the dot products themselves can grow really large in magnitude, either positive or negative.
Okay. And that's bad because...
Because it pushes the softmax function into regions where the gradients are incredibly tiny. Vanishing gradients. It makes learning really difficult, or even impossible.
Ah, so the gradients get saturated.
Right. Dividing by the square root of dk counteracts this effect. It scales the dot products back down, keeping the inputs to the softmax in a nicer range with healthier gradients. The paper explicitly notes this scaling is crucial for stable training, especially with larger dimensions.
Okay, that makes a lot of sense. Stabilizing the training. Now, that's scaled dot product attention, but they use multi-head attention. Why not just use one big attention calculation? Why multiple heads?
Good question. They found it was beneficial to, instead of doing one single attention calculation with the full D-model dimension vectors, project the queries, keys, and values multiple times using different learned linear projections.
So you take your Q, K, V vectors and transform them, say, 8 different ways.
Exactly. In the base model, used H8 heads, so you get 8 distinct sets of projected Q, K, and V vectors, each with a smaller dimension. DK, DV, DVODL is a 5, 12, 8 equals 64.
Okay, so 8 smaller attention problems instead of one big one.
Right. And then you run the scaled dot product attention function on each of these 8 sets in parallel. These are your 8 attention heads.
And the benefit of doing that is?
The intuition is that each head can learn to attend to different types of information or different aspects of the relationships between words from different representation subspaces, as the paper puts it.
So like one head might focus on syntactic links, another on semantic similarity, maybe?
Potentially, yeah. Or one might look at nearby words, another at distant dependencies. If you just had one big attention mechanism, you'd be averaging all these different signals together, which might wash out some of the finer details. Multi-head allows the model to jointly attend to information from these diverse perspectives simultaneously.
That's really clever. And computationally, is it much more expensive?
Actually, no.
Yeah.
They designed it so the total computational cost is roughly similar to having a single attention head with a full D-model dimension.
Mhm.
You do more projections initially, but the attention calculations themselves are on smaller vectors.
Okay, so you run the 8 heads in parallel. How do you combine their outputs?
You just concatenate the output vectors from all 8 heads and then apply one final linear projection to get it back to the original D-model dimension.
Got it. So just to recap, where exactly do these multi-head attention mechanisms show up in the transformer architecture?
Right, there are 3 distinct places, as we touched on. First, in the decoder, there's the encoder-decoder attention. Here, the queries come from the previous decoder layer, but the keys and values come from the output of the encoder stack.
That's the one letting the decoder look at the input sentence.
Exactly. Second, there's encoder self-attention. This happens within each layer of the encoder. Here, the queries, keys, and values all come from the output of the previous layer in the encoder.
So each word in the input representation can look at all the other words in that same representation, building context.
Precisely. It allows the encoder to build representations that incorporate context from the entire input sequence. And third, there's decoder self-attention.
Which is like the encoder self-attention, but in the decoder.
Yes, queries, keys, and values all come from the output of the previous decoder layer.
Yeah.
But this is the one where that crucial masking happens.
Right, preventing positions from attending to future positions.
Correct. To maintain that autoregressive property needed for generation.
Okay, that covers the attention mechanisms in detail. What other essential components make the transformer tick?
Well, there are the position-wise feed-forward networks. We mentioned these briefly. They sit inside each encoder and decoder layer right after the attention sublayer.
And these are applied position by position.
Exactly. It's the same simple, fully connected feed-forward network applied independently to the vector representation of each position, each word token, basically, in the sequence.
So the network that processes the vector for cat is the same one that processes the vector for sat, just applied separately.
Yes. It typically consists of 2 linear transformations with a ReLU activation function in between. The paper used an input-output dimension of D-Model 512 and an interlayer dimension DFF 2048.
So it expands the representation, applies nonlinearity, then contracts it back down.
Right. You can sort of think of it like applying 2 one-by-one convolutions across the sequence dimension. It adds nonlinear complexity per position.
Okay. And then there are the more standard bits, like embeddings and the final softmax.
Exactly. Standard learned embeddings convert the input and output tokens, words or subwords, into those D-Model 512 dimensional vectors.
And at the very end of the decoder stack.
After the final decoder layer, there's another linear transformation followed by a softmax layer. This converts the decoder's output vector for a given position into probabilities over the entire vocabulary, telling you which word is most likely to come next.
Standard practice for generation. They mentioned sharing weights here.
Yeah, a neat little trick. They shared the same weight matrix between the token embedding layers, both input and output, and that pre-softmax linear transformation, just scaled by the square root of D-model, saves parameters.
Now, this is really critical. We've established the transformer has no recurrence, no convolutions, so intrinsically, it doesn't know if the cat-sat is different from sat-cat. How does it get word order information?
Ah, yes, that's where positional encoding comes in. This is absolutely crucial. Since the model architecture itself doesn't track sequence order, they explicitly inject information about the position of each token.
How do they do that?
They create these special vectors, the positional encodings, that have the same dimension as the embeddings, D-model. Then, they simply add these positional encoding vectors to the corresponding token embedding vectors at the very bottom of the encoder and decoder stacks.
So each position, first word, second word, etc., gets a unique position vector added to its word embedding.
Exactly. And they didn't learn these vectors. They used a fixed mathematical function based on sine and cosine waves of different frequencies.
Sinusoids? Why that specific function?
The hypothesis outlined in the paper is that using sinusoids might make it easier for the model to learn to attend based on relative positions. For instance, the relationship between the encoding for position I and position I plus k could be represented by a linear transformation, which might be easy for the model to learn.
Interesting. And potentially it could help generalize to sequence lengths longer than those seen during training, maybe.
That was another hope, yes. Because the function isn't learned from the data, it can generate encodings for positions it hasn't seen. They did also experiment with learned positional embeddings, though.
And how did those compare?
On the tasks they tested, the learned embeddings produced results that were nearly identical to the sinusoidal ones. But they stuck with the sinusoidal version for the main results, perhaps because of that potential generalization benefit.
Okay, so we have the architecture. Stacked layers of multi-head self-attention and position-wise feed-forward networks, residual connections, layer norm, plus positional encodings to handle order. Now, big question. Why did this attention-only approach work so much better? The paper makes a pretty compelling argument by comparing it on three key aspects.
It does. They look at self-attention versus recurrent and convolutional layers. First up, computational complexity per layer.
How much work does each layer do?
For self-attention, the complexity is roughly proportional to the sequence length squared, and so it's the representation dimension d. So OND.
Okay, n squared. That sounds potentially expensive if n is large. How does that compare?
Recurrent layers are typically OND, and convolutional layers, with kernel size k, are often OKND, although deeper ones can be OKND.
So self-attention's n hertz for very long sequences, but the DVSD factor helps it. If your sequence length n is smaller than your representation dimension d, which it often is for sentence-level tasks where n might be dozens or hundreds and d is 512 or 224, then self-attention can actually be faster per layer than recurrent models.
Exactly. But the real knockout punch comes from the second metric, amount of parallelization, measured by the minimum number of sequential operations required.
How many steps do you have to wait for?
For recurrent layers, you have to process step by step, so it's ON sequential operations. You can't compute step 5 until you have step 4.
The fundamental bottleneck we discussed.
Right. Convolutional layers are better. You can parallelize across the sequence, but linking distant positions still requires information to propagate through layers, so the path length might be logarithmic, own log n, or depend on kernel size. But self-attention.
What is it for self-attention?
Oh, constant time. You can compute the attention for all positions simultaneously in a single step within a layer because every position can directly look at every other position.
Wow. O1 sequential operations.
Hello.
That is a massive advantage for training speed on parallel hardware like GPUs.
Huge. And that ties into the third metric, maximum path length for information flow between any two positions in the sequence.
How far does information need to travel to connect distant parts of the input?
In a recurrent network, connecting position I to position j requires traversing ij steps, which is O at, in the worst case, across the sequence.
Yeah.
Long path.
Okay. Convoluted.
Better again, stacking layers reduces it, maybe O log or I log n. Similar to the sequential operations, but again with self-attention.
Don't tell me it's O1 again.
It's O1 again. Every position is directly connected to every other position within a single self-attention layer. The path length is constant.
So short path length, making it easier in theory to learn long-range dependencies, and massive parallelization allowing for much faster computation per layer.
That's the core argument. The transformers architecture, with O1 sequential operations and O1 maximum path length via self-attention, gives it fundamental advantages in both training speed and the ability to model long-range relationships compared to traditional RNNs or even deep stacks of CNNs.
Okay, the theoretical advantages are clear. How did they actually train this thing, and what were the results in practice? Let's talk training setup first. Datasets.
They primarily use the WMT 2014 English to German dataset. That's about 4.5 million sentence pairs. And also the larger WMT 2014 English to French dataset, which has around 36 million pairs.
And they used word pieces or byte pair encoding, subword units.
Yes, standard practice to handle large vocabularies and rare words. Byte pair encoding was used.
How did they batch the data for training?
They grouped sentence pairs together that had similar lengths. This minimizes the amount of padding needed, making training more efficient. Each batch contained roughly 25,000 source tokens and 25,000 target tokens.
And the hardware must have needed some serious compute.
Well, by today's standards, maybe not that serious, but significant for the time. They reported training on a single machine equipped with 8 NVIDIA P100 GPUs.
Okay, 8 GPUs. And training time.
The base model, the one for the parameters we've mostly discussed, N6 layers, D model 5 to 12, trained quite fast, about 12 hours for 100,000 steps.
12 hours. That's pretty quick for a state-of-the-art translation model back then.
It really was. They also trained a big model with larger dimensions, D model 124, DFF 4096, H16 heads. That took longer, around 3.5 days for 300,000 steps.
Still impressive. Optimizer. Atom, I assume.
Yep, Atom, but with specific beta parameters, beta 1.9, del 24.98, and epsilon 10 naught. And they use a particular learning rate schedule.
Ah, right. Not just a fixed learning rate.
No, a dynamic one. It increased linearly for the first few thousand steps. They used 4,000 warm-up steps, and then it decreased proportionally to the inverse square root of the current step number.
So start slow, ramp up, then gradually decay. That's pretty common now, isn't it?
It is. This kind of schedule became very popular, partly thanks to this paper.
And regularization, always important to prevent overfitting, especially with big models.
Absolutely. They used two main techniques. First, residual dropout. They applied dropout not just anywhere, but specifically to the output of each sublayer before it was added back to the sublayer input, the residual connection, and normalized.
Okay, targeted dropout.
Yes, and also to the sums of the embeddings and the positional encodings. The rate was p-drop equal 0.1 for the base model.
And the second regularization technique?
Label smoothing. They used a value of epsilon equal 0.1.
Label smoothing. That's where you don't train the model to be 100% certain about the correct target word, right? You make it predict the correct word with slightly less confidence, like 90%, and distribute the remaining probability mass slightly over other words.
Exactly that. It's counterintuitive, maybe? They note in the paper that using label smoothing actually hurt perplexity. Perplexity is a measure of how uncertain the model is. Lower is a better. So the model became less sure of itself. Right. But it consistently improved the final translation quality, measured by accuracy and, crucially, the BLEU score.
So less confident predictions internally, but better overall translation results. That's a fascinating trade-off.
It really is. It seems to make the model less prone to making overconfident, potentially brittle predictions.
Okay, so that's the setup. Let's get to the punchline, the results. Machine translation first. WMT 2014, English to German. How did the transformer do?
This is where it really stunned people. The big transformer model achieved a BLEU score of 28.4 on the standard News Test 2014 benchmark.
28.4 BLEU. How good was that at the time?
It wasn't just a new state-of-the-art for a single model. It beat the previous best results, which were typically achieved by ensembling multiple different models together, by over 2 full BLEU points.
Wait, a single transformer model beat ensembles of the previous best systems by 2 points. That's huge in translation benchmarks.
It was absolutely massive, a real breakthrough moment. And even their base model, the one that trained in just 12 hours, it scored 27.3 BLEU. That alone surpassed all previously published models and ensembles. And it did so at a fraction of the training costs reported for those previous systems.
Wow. So faster training and significantly better results. What about English to French, a bigger data set?
Similar story. The big transformer achieved 41.8 BLEU on the WMT 2014 English to French NUSTIS 2014 set. Again, a new single model state-of-the-art.
And the training cost comparison.
They highlight in the paper that this was achieved using less than 14 of the training computation reported for the previous state-of-the-art model on that dataset.
Unbelievable. Faster, cheaper, better. That's the trifecta.
Pretty much sums it up for translation, yeah.
Did they try it on anything else to show it wasn't just a translation miracle?
They did. They applied it to English constituency parsing. This task is quite different. It's about understanding the grammatical phrase structure of a sentence, like identifying noun phrases, verb phrases, etc.
More structural, less direct sequence to sequence. How did RNNs usually do on this?
Parsing can be challenging, especially with limited training data. The paper notes RNNs had struggled in some small data regimes for this task previously.
So how did the transformer fare, given it wasn't specifically designed for parsing tree structures?
It generalized surprisingly well, even with minimal task-specific tuning. They trained it on the standard Wall Street Journal, WSJ, parsing dataset.
And the results?
Using only the WSJ training data, their transformer achieved an F1 score of 91.3 on the standard test section, section 23. F1 is a common metric for parsing, balancing precision, and recall.
91.3 F1. How does that compare?
That score actually outperformed the well-known Berkeley parser, a strong statistical parser at the time.
Wow, okay. And did they try it with more data?
Yes. In a semi-supervised setting, leveraging additional unlabeled data, the transformer reached 92.7 F1. This score surpassed the previous state-of-the-art results for semi-supervised parsing models.
That parsing result is really important, isn't it? It shows the core architecture, the attention mechanism, wasn't just a one-trick pony for translation. It had broader applicability to sequence understanding tasks.
Exactly. It demonstrated the general power and flexibility of the attention-based approach.
The paper also includes some analysis varying parts of the model to see what really mattered. What insights came from those ablation studies?
Right, they tweaked components of the base model. For instance, they looked at the number of attention heads and the dimensions used within each head,
Hmm.
dk, dv.
What happened when they changed the number of heads?
Using just a single head performs significantly worse, about zero point 0.9 BLEU points lower on English to German, so multiple heads clearly help.
But is more always better?
Interestingly, no. They found that increasing the number of heads too much, while keeping D model fixed, meaning dk and dv per head gets smaller, also caused performance to drop slightly. They tried H16 and H32, and both were a bit worse than H8.
So there's a sweet spot. It suggests the value isn't just parallelism, but having enough capacity within each head's perspective.
Seems likely, yeah. The multiple focus perspectives are valuable, but each perspective needs enough representational power.
What about just reducing the key size, DK, while keeping the number of heads constant?
That also hurt performance noticeably. Reducing dk degraded quality.
What does that imply?
It suggests that the compatibility function, how the query and key interact via the dot product to determine attention weights, isn't trivial. It benefits from having sufficient dimensionality to capture complex relationships. It's not just about pointing, it's about how you determine where to point.
Makes sense. And bigger models generally did better, I assume, like increasing D model, DFF number of heads.
Yes, the big model consistently outperformed the base model. That's a pretty standard finding in deep learning. More capacity often leads to better results, provided you can trade it effectively and avoid overfitting.
Speaking of overfitting, how important was dropout?
Very important. They explicitly state that dropout was very helpful in avoiding overfitting. Makes sense for a powerful model trained on finite data.
And finally, that positional encoding comparison, again, sinusoidal versus learned.
Right. As we mentioned, they found that learned positional embeddings gave almost identical results on their development sets, but they stuck with the sinusoidal function for the main paper results.
Why again?
The theory was that the sinusoidal version might generalize better to sequences longer than those seen during training, because the function itself can extrapolate. They didn't definitively prove this in the paper, but it was a reasonable hypothesis.
Okay. Beyond the raw performance numbers and ablations, one really cool aspect the paper touches on, even if briefly, is interpretability. Can we actually look inside and see what these attention heads are learning to do?
Yes, and this is one of the nice side effects of attention mechanisms. They're somewhat more interpretable than, say, the hidden state of an LSTM. The paper includes visualizations of attention distributions.
What do those visualizations show?
They show which parts of the input sequence, or previous parts of the output sequence, a given word is paying attention to, often broken down by attention head. And the fascinating finding is that different heads seem to learn to specialize in different tasks or focus on different linguistic phenomena.
Like what kind of specializations?
Well, some heads appear to learn things related to syntactic structure. For example, they might consistently have a word attend strongly to its grammatical subject or object, even if they are far apart in the sentence.
Capturing those long-range dependencies visually.
Exactly. Other heads might focus more locally, perhaps attending strongly to the immediately preceding or succeeding word. Some heads seem involved in resolving ambiguity or co-reference, like making sure a pronoun it attends strongly to the noun it refers back to, the cat.
So the model isn't just a black box. The attention weights give you a window, albeit a complex one, into how the model is relating different parts of the sequence, and it seems to often align with structures we understand linguistically.
Precisely. It doesn't give you the full story, but it provides valuable insights that are harder to get from purely recurrent models.
Okay, so let's bring it all together. What's the fundamental takeaway from attention is all you need? What did it really change?
I think the core message was incredibly powerful. It demonstrated that you could achieve not just good, but state-of-the-art results on really complex sequence transduction tasks, like machine translation using only attention mechanisms. You didn't need recurrence or convolution as the primary sequence processing tool.
And crucially, doing so allowed for models that could be trained significantly faster due to parallelization.
Absolutely. It broke that sequential bottleneck, so it validated the power of attention as a fundamental building block for sequence modeling. The title wasn't just catchy. For these tasks, attention really did seem to be, well, maybe not all you need, but the core ingredient you couldn't do without.
And the impact since then has been astronomical. Transformers are everywhere now. The paper itself hinted at the future beyond text, didn't it?
It did. Right at the conclusion, they mentioned plans to extend the transformer to handle inputs beyond text, things like images, audio, and video. They were already thinking about generalizing this parallel attention-based processing.
And that really leaves us with a fascinating thought, something for you, the listener, to mull over. The core innovation here was shifting from processing sequences step by step, like RNNs did, to a model that can instantly connect any element to any other using attention. How might this fundamental change, moving away from sequential processing towards parallel global attention, reshape how we design AI systems, not just for language, but for understanding any kind of data? Think about images, audio, maybe even complex simulations. What does it mean if AI can perceive the whole picture all at once, relating any part to any other instantly? It really opens up a different way of thinking about artificial perception and intelligence.